Have you heard the universe is expanding? Most people have, but they haven't thought about it in some way, and they might have some questions about it. So this lecture will try to delve into the expanding universe, what it means to be expanding, what's expanding, things like that. So you've mistakenly stumbled onto extraordinary concepts in physics, and I'm Professor Robert Nemiroff, lecturing at Michigan Technological University in the beautiful Upper Peninsula of Michigan. So this is a series of lectures that no textbook is required for. You're welcome if you just stumbled onto this, although people are getting credit for watching these, strangely enough. You can find a list of these lectures online here. If you can read that, good for you. Otherwise, search for these buzz phrases. Okay. So in order to understand, or better understand, the expanding universe, which may or may not be fully understood, there are several key concepts which I reviewed in a previous lecture, so this is not completely deja vu. One is the cosmological principle, which says the universe is homogeneous and isotropic. So homogeneous means that it's the same everywhere. So we can come up with a universe that is chunky everywhere, and it would probably be much more accurate than these models of the universe that we have the same everywhere. But the chunky everywhere, different densities everywhere, those are much more complicated. If you have it the same everywhere, you just need one number to say what the density is. If you have it chunky everywhere, then you're going to have all these different numbers for all the places in the universe and describe how every different place in the universe evolves. But if you just have one number, it's easy. And it turns out you can get significant insight from using one number. There's a Jell-O analogy, so go have Jell-O. Another one is isotropic, so things look the same in every direction. So you might have noticed in your life that things don't look the same in every direction. If you did, good for you, you're astute. However, if you were to average over every direction, so right now you might be looking where it's light, and if you look over there, you look where it's dark, pretty much things would average out to be some color beige after a while, because everything turns out to be beige. So if you look dark in one direction, then a few minutes later it's light in that direction. It depends where you move your head to. It depends if you're depending on the direction of your head. Everything's going to average out. So on the long time scale, it's isotropic in every direction. So we consider a universe that is isotropic in every direction. It's much easier to do that as well. So people have noticed that it's brighter in the direction of the sun. But we happen to be lucky to be near the sun, lucky in the sense that it gives us life. And if you turn the sun off, we'd all die and stuff. But if you go far enough into the universe such that there's no specific star that's all that much bright, and then you spin around and you wait for long enough, pretty much every direction will look the same, and that's what we mean by isotropic. So those universe models are relatively simple and can be committed to paper and evolved, and its insight can be gotten. So Einstein understood that the universe could be infinite, and he created his general relativity in about 1915 is when it was published, but he was thinking about it for many years before that. Einstein was troubled by the universe implied by general relativity. He was worried that it would collapse in on itself. And if it collapsed in on itself, then you wouldn't be able to have the Jell-O that I suggested before. So he, at one point, postulated something called a cosmological constant, which would be a repulsive force everywhere in the universe to keep the universe from collapsing in on itself. But to his surprise, and Einstein called it his greatest blunder, an astronomer, Edwin Hubble, didn't come up with the idea. He had really big telescope available to him, and he looked at these spiral nebulae out there, figured out that they were galaxies like our own, and then figured out that they were moving away from us. That most, not all, most spiral galaxies, or galaxies out in the universe, have what's called a redshift, which means that you can look at their wavelength bands that we know in our laboratory here. Let's consider hydrogen. Hydrogen glows very brightly in very, very specific colors. But then you look at a galaxy that's far away, and it glows in the same pattern of colors as hydrogen, except they're all slightly shifted to the red end. What could that be? Well, if the universe is expanding, if you think of it in terms of a simpler Doppler effect, which isn't always the best way to think about it because there's several things that can cause a redshift, if the universe is expanding, then things become redshifted. So all these galaxies, and the smaller the galaxies were, the more redshifted they were. So based on that, Hubble discovered the whole rest of the universe, essentially, and that the universe is expanding. And when Einstein heard this, he didn't say, oh, that can't be right. He said, oh, duh, I should have thought of that. Should have thought the universe was expanding, but I didn't. Einstein had a static universe. Hubble even created a simple model for the galaxies he saw, that a galaxy's velocity away from us is proportional to its distance away from us. And it's proportional through a constant, which is now called Hubble's constant. I don't know if he himself referred to it as Hubble's constant. People are usually too modest to do things like that. Here is a plot. Hubble then got out a picture of many of his galaxies and made some lines on it. And so he plotted the distances to galaxies as a function and plotted velocity on the y-axis. And he saw that with these green dots that the further away they are, the faster they were moving. Eventually people said that these galaxies were too confusing, and so he removed them and used regular graph paper. But the Hubble's constant, the Hubble's law, as it's called, stood. Strangely enough, when they got better data, they found out that what Hubble's constant is changed greatly from what it was in the beginning. So Hubble probably had a lot better data than he published in his initial papers, which is a cool thing in science. Sometimes people try to be very conservative and confirm things well beyond what they're willing to publish at first, which I believe Hubble did, and it served him well. Because Hubble's law stands today, even if the original data, this is a subset, wasn't as convincing as we sometimes historically believe it was. So, here's one of the key questions that people like to ask. What is our universe expanding into? We just said the universe is expanding, right? So what's going on? Is it expanding into empty space? Is there a lot of empty space out there and the universe just expands into it? So here we have, oh, stop. I'm sorry. Please stand by. I don't know why I did that. Let's hope I can go to the next slide. Is our universe like this and moving out, and there's all this empty space out there, which the universe will soon expand out into? Is there another dimension? So we're familiar with 3 dimensions in this classroom in places around us right now, but maybe there's more spatial dimensions. Maybe we're expanding into those spatial dimensions. Is there an extra time dimension? So we're familiar with common time, that we look at our wristwatches or clocks or the computer monitor, or sometimes on the upper right. Is there another time dimension that we're expanding into? Or does general relativity only say that objects can move apart? It doesn't really say more. But bump, freeze it, have a sandwich, come back. Welcome back. General relativity really only says that objects can move apart. It tries to use as few variables as possible. So its density for the universe includes homogeneity and isotropy. So there's only one density for the universe, and it's the same in every direction. So general relativity really only says that the energy density is changing at time. And since there's only one everywhere in the universe, it's changing everywhere in time. So general relativity doesn't really fully address this. There are theories that use other spatial dimensions. String theories, for instance. But Einstein's general relativity, GR, by itself isn't one of them. And that's the one that makes the best predictions right now for what we can use. GR says the entire universe could be expanding. It doesn't include any empty space it's expanding into. There is no provision for that. We'll hear at the end of this lecture, that's more of a Newtonian concept. The universe is the same everywhere, according to the equations of general relativity. And things are expanding away from each other, but they're not necessarily expanding into an empty space. It's essentially diluting. Okay, one way to think of this that's in several books is that you have raisin bread. And this raisin bread was dense originally, and then you cooked it, and the raisins expanded. What I don't like about this is that it keeps the hypothesis that there's empty space around the raisin bread that the raisin bread is expanding into. And general relativity doesn't include an empty space like that. So here's another question. Here you go. Quiz your friends and family members. Quiz your dog. You know where he is, he or she. To which direction is the center of the universe? I get this question a lot. Is it the sun? Is the sun the center of our universe? Is the center of our Milky Way galaxy the center of our universe? Is the dipole hotspot on the microwave background, is that the center of our universe? Or is there no direction that is the center of our universe? Okay, you can phone a friend. You can poll your studio audience. If you have a studio audience, please poll them now. Okay, Here we go. There's no center. General relativity, which explains things better, cosmology better than any theory, has no center. There's no equation for this is the center. There is no, and this is one of my favorite phrases, Big Bang National Park. You cannot go on a field trip to Big Bang National Park and stand where the universe started expanding from. Can't do it. The universe is not an exploding golf ball, according to general relativity. And it doesn't even work if you try Newtonian gravity and try to have an exploding golf ball. It doesn't even work then. Every point can be considered the center of the universe. And the expansion will look the same from every point, according to general relativity. Here's possibly a better one by reducing our dimensions from 3, which we know we live in 3 spatial dimensions. Let's pretend we lived in 2. And we are now on an expanding golf ball, but we're confined to the surface of this golf ball. Then the whole golf ball, the whole thing expands. And if people were to ask which point on this is the center, the answer is, I don't know. They're all the center. This fits better with the general relativistic concept than an exploding golf ball where the pieces go off in every direction. Another way to look at this is blowing a balloon up. So here you have, again, we're confined to the surface of this balloon. This is a dimensional analogy. You can tell it's at 3 dimensions because there's a window reflected there. Here's the reflections here. So this has constellations on it, although maybe I recognize some of them. I think this is Perseus. But anyway, so the universe, there is no place on this balloon that you could have considered the center. But things are expanding, and every place on the balloon was more dense in the past. Now, this gets interesting because if you think of things in a Newtonian sense, if you have a Newtonian cosmology, let's say you don't believe this GR stuff, which works really well, GR explains Redshifts tremendous cosmological theory, which is so simple. But if you consider a more complicated theory, Newtonian cosmology, where, say, you have an explosion where little fragments go out in every direction, and as they go out, the average density becomes less dense, then you might come to the conclusion, well, let's look at this space right here. And let's put ourselves in the center of that. How would things look from there? The answer would be, oh, it would look pretty good, actually. You would get things that are further away moving further away from you. Another way to look at this is, let's say you run in a marathon, and you're running, and then you notice people spread out during a marathon. So the fast people go to the front, and the slow people end up in the back, and the people in the middle, which is, I'll assume, where we are, we see people still around us. Assume everybody runs at a constant speed. Even then, the further you are away from somebody, the further they're moving away from you. So if you renormalized your speed to 0, you would see everybody moving away from you. But the problem with Newtonian cosmology is we don't see the gravity of an edge. That's one of the major problems. We don't see the gravity of an edge. So Newtonian cosmology doesn't work for that and other reasons. It's not a relativistic cosmology. You and I do not expand. Another misconception is that people expand themselves as the universe expands. We don't. Our molecules hold us together strong enough that we don't expand. Don't worry about it. We're constant. It's the galaxies that are not bound to each other like that are doing that. So you're not going to expand, but the universe will continue to expand into the indefinite future, and it is expanding strangely, and we will get to that in future lectures. So until then, I will see you later.